algebra students. I'm here with you today to introduce exponential functions. They're one of the most applicable types of functions, in my opinion, in algebra. They are used to model many types of behavior, and they have a lot of applications we'll explore in future lectures. So to begin with, we'll kind of start at looking what an exponential function is. And in our current situation, it's really applicable to the spread of a virus. So we'll see how we can model these equations and apply them to things like population increases, spreads of viruses, radioactive decays, and more. Okay, to start, an exponential function, what is it? It's a function, and my notation for a function is just f of x for short, that models rapid growth, things that grow really quickly, and or a slow decline, decay. Okay, so it's a really vague general behavior that we're looking at right here on how we're defining exponential functions. So the idea is that these types of functions have an independent variable that grows proportionally with the dependent variable. So we could also say it's a function in which, it's a little more formal, the independent variable changes or yields, let's use that word, yields a proportional change. So this is going to be a percent increase or decrease, proportional change in the dependent variable. Okay. So we typically use x for our independent variable and y for our dependent variable. Okay, that's a little more formal way of defining an exponential function. So here are some illustrations of exponential curves. Okay, so this would be something that would reflect rapid growth, okay, exponential growth. So typically if we're taking data and we were graphing that data, let's say in a science experiment or a lab, we would identify this as an exponential function if we had points that were laid out and we had something that started to climb really quickly. Okay. For instance, like the spread of a virus, it would climb very quickly. It would start with a few cases and it would just grow exponentially from there. Okay, that's an example when those types occur. So this is y, or again f of x, and then we have exponential decline, so slow decay or decline, exponential decay. A typical pattern in the graphs will be that starts out fairly large and then slowly reduces its amount but never gets to zero. And of course that's going to depend on a lot of parts of the function. So just the main type of exponential decay function will go towards the x-axis. Okay, so a curve like this expresses exponential decay, and something like the value of an object that depreciates over time, the radioactive decay of certain isotopes, let's say like carbon-14, it disappears, but never goes away. Okay, so we'll look at some of those types of applications. So those are the basic kinds of curves it'll generate. And again, those will vary depending on the function. So let's go and write some of the behaviors. So some of the behaviors that exponential curves model will be, so for growth, we can think of population. You have a small population, let's say, of rodents. It could quickly grow exponentially given time and no predators. But we have population growth. As mentioned before, we have the spread of a virus. We have interest on certain accounts. It could grow exponentially depending upon how it's set up, how it's compounded. Interest growth. And let's see, a few others. We have computer processing power. We have bacteria growth. Bacteria can grow really, really quickly. And those are some of our main ones. Okay. You can look those up, and there's plenty of good stuff there to model. So that's growth. So decay, decline. My favorites are looking at radioactive decays. One of the milestones in science, because it allowed us to date and understand nuclear processes. So lots of good information there. Radioactive dating, radioactive decay. We also have depreciation and interest, depreciation and value. Let's see if I have any more written down. Nuclear chain reactions. Atomic half-life. Nuclear chain reactions. Etc. Okay. So those are typically some of the main examples used to modeling that type of behavior. So, if I give you a quick little illustration here, okay? Maybe you start out with a pair of rabbits, and that doubles to 4, and then that doubles to 8, and then that doubles to 16, and that doubles to 32. That would model population growth. A decay would be, let's say you had carbon-14, which we denote by C14. It has a half-life of 5,730 years. And carbon-14 is used for a lot of dating in the thousands of years range, tens of thousands of years range. So it's used a lot in archaeology for dating tools and objects. And what happens is, what this means is that if you started out with, let's say, 100 grams of it, okay, what would happen is, okay, if you had 100 grams, you had 100 grams of carbon-14 at time 0 years. What would happen is in 5,730 years, you would have 50 grams. Okay? And I should say the amount. What would happen is 100 grams at 0 years. In 5,730 years, you'll have 50 grams. And double that, which would be 11,000. Let's see, 60. 11,460 years, we'll have 25 grams, and onwards. That's what we mean by half-lives. Okay, and we'll come back to this. I'm just giving you a little overview here. So if you start out with 100 grams, 11,000 plus years later, you'll end up with 25 grams, and then you'll have half of that in another 5,730 years. Okay, this is a really common isotope used for radioactive dating. Okay, so let's get to some of the main formats we'll be looking at. Okay, so let's take a look at our template that we use for exponential functions. When we have exponential data we're working with, we have a certain template. So we have a general form of an exponential function. Okay, the general form of an exponential function is that we have our dependent variable equal to a to the x power. Okay. So the condition is a cannot equal 1, otherwise it won't be exponential. And the other condition we have is a must be a real number. It belongs to the real number set. So this is a really important template we use. And there's going to be many variations. We'll look at some of the variations that we use for interest modeling. Okay. So we have some alternative forms. Some of these alternative forms will be a equals a naught times e, which is a number to the kt. This is what we use for radioactive decays or interest. We have a more specific model where this is your initial amount and it grows exponentially based on this factor in the exponent and gives you a certain amount output. Okay. And then we also have, a lot of times what we have plus or minus a plus or minus kx. Many times we'll have this k value in the exponent, and we look at what that k value is, and it tells us how the exponential function grows or decays. If it's positive, it's a positive k, it'll grow. If it's a negative k, it'll decline. And these are just general trends because you also have to look at what the base value is. So the most important thing here is that you have a base and the x is in the exponent. Okay, very, very important. dot, dot. There's some other variations out there, but those are the most common. Okay. Now what we have to realize is that every exponential gives rise to an entire family of functions. And I'll give you some number examples. So what we have to know every exponential function with a unique base value, a, gives rise to a whole family of functions. So what we like to do in algebra, we like to identify a parent graph, and then we see what numbers are added or subtracted in the exponent or outside to see how it's going to move left, right, or shift up or down, or how it's going to reflect. So some examples. Number one, here's the most commonly used exponential function. F of x equals 2 to the x. This is a parent with your base a equal to 2. Okay. Has families such as, let's say f of x equals to the x minus 1. Okay. We could have another function generated based on that parent. Let's say we have 2 to the x plus 3. We could have several others. F of x equals 2 to the x minus 1 plus 3. And dot, dot, dot. We could go on ad infinitum, finding a whole bunch of curves generated from this one parent graph. Okay. Interesting thing to know. Now, some other types of exponential functions. We'll look at some of these that are base 10. They're very popular, 10 to the x power. So we have a different base now. And 2, if we had f of x equals 1/10 to the x power. Now this one is a little tricky because when you have a function that's exponential and its base is a fraction, it's the same as having a negative exponent. So note, this is equivalent to 10 to the negative 1 to the x power, which is equal to 10 to the negative x. So there's two ways of writing this function. So what you want to do is get it in the non-fraction form and then identify this as a decline, an exponential decay or decline function. So those could be a little tricky. So when you have a fraction, my advice is to convert it, and that way you could understand the trends produced by that function a little more. Okay. So, and we're not left with just fractions, we can have decimals. Okay, those are common. When you're looking at spreads of viruses, you have an R value that tells you how transmittable that virus is, and you put those values in for your base or use them as coefficients. So depending upon how the model works, there's several different values you could put in for your base. And in other places, you can have a very common base that's used. This is E, and that is Euler's number. e to the x, and e, when we get to that, e is approximately the value 2.72. I'll just say 2.7 for now. Okay, I'll have to look up that second decimal place. And that's Euler's number. It's a very common base use. So it's one of these transcendental numbers that you just have to know and you'll be exposed to a lot especially in exponential modeling and log functions. Okay, so let's go ahead and look at what this e value is. Say dot, dot, dot. There's an infinite variety out there. So let's define e. Okay. E, as I stated, this is a transcendental number. So it has a specific definition. Okay, they're non-algebraic from the polynomial root, from the polynomials. We also call this Euler's number. Okay, and E is approximately, I'll give you a better approximation, 2.718. Most calculators have the value of E stored in them, and you just pull it up. So you can use approximation. If you need to, okay, but you can get that exact value, use that exact value stored in your calculator. And E, the way we use E, it's a base amount. It's a really important function in mathematics, shared by all continually growing processes. Basically, it's what we call a unit of growth. And it comes into play especially with the compounded interest functions. When we're compounding interest every second of every day, every microsecond of every day, it tends to this E curve that we'll talk about. Okay, so some neat tidbits. Where do we get this number? Oh, there's several ways. You're not responsible for knowing this, but one is a limit value. The limit as n goes to infinity of 1 plus 1 over n to the n. We'll give you an approximation for E, and this is approximately 2.718. Okay. 2. There's another definition used, and that's a sum of terms of 1 over n factorial. And this goes to 2.718. And here's another nice little relationship related to complex number. E to the I pi equals -1. So this is a very interesting relationship between E, your complex number I, pi, and all of that equals -1. Okay? So that's where it comes from, or those are some of your standard definitions. You could also define it through your graphs and your curves. But for us, all we really need to know is our numbers, the approximation for E. And know that it is between the curve 2 to the x and 3 to the x, because it's 2.718. Okay, so here's some examples. a look at some graphs. And let's start with number 1. F of x equals 2 the x. And some of these could get very messy, and I would encourage you to practice doing a table of values and getting as much of a sense of the exponential function as you can. So let's go ahead and take a look at our table of values here. X, y, or f of x. Okay. And just knowing that the general curve will be rapid increase will really help me understand this. Now this is a real basic function. I'm looking for negatives anywhere in this function, and I'm looking for any numbers added or subtracted. I don't see any of that here. So it's going to be a real basic one. So I'm going to start with 0. If x is 0, then y is going to be 2 to the 0, which equals 1. So that produces the ordered pair of 0, 1. Okay, 0 is always nice to have in the exponent because it outputs the value 1. If I have 1, I get 2 to the first power, which is equal to 2. And I get the ordered pair 1 comma 2. If I put 2 in the exponent, I get 2 squared, which is equal to 4. And I have the ordered pair 2 comma 4. If I put 3, I get 2 to the third power. I get 8. 2 comma 8. 3 comma 8. And let's go ahead and see some of the negative values. We can see that this is doubling. Okay, it's growing exponentially. Our output is growing as a percent increase with respect to our input, our independent variable. Now, what happens if I put a negative 1 in there? I get 2 to the negative 1, which is 1/2. And I get the ordered pair negative 1, 1/2. Okay. What happens is I go more negative. Well, your fraction gets smaller. So you get negative 2 comma 1/4. Squishing that in there, hopefully you could see. But you could follow along with my voice too. Now if we do a sketch, what we have is something that's growing rapidly along the y-axis. Okay? And so the trend I want to show is this rapid increase. Now 2 is not that big of a base, but if it were 10, I'd want to adjust my spacing. Okay, so here I have 4, 4, negative 4, negative 4. Okay, so if I plot some of my ordered pairs, I have 0, 1, 1, 2, 2, 4, 3, 8. So you can see that I'm quickly running out of room up here. Okay, I have to extrapolate or extend my line upward exponentially. Negative 1, 1/2. Negative 2, 1/4. And if I continue along this negative route, you notice that you're going to get closer and closer to the x-axis, but you'll never cross. That's called asymptotic behavior. We'll have this asymptote at x equals 0. So when we plot this now, so really it should be a little bit more up here. We get this exponential growth curve. And you can label some of these points. So here we had 1, 2, 2, 4. And what you see is this doubling process of your output. 3, 8, and onwards. Okay. So this sketches to the x power. Okay, so what I'm going to do is add a little bit here. If I had some extras added on to my 2 to the x function, let's say I went ahead and did 2 to the x minus 1, and I subtracted 3 from it. Okay, so our next example, we're going to do another exponential function. So this is a part of a family of functions of the 2 to the x curve. In this case, we're going to go ahead and add a minus 1 in the exponent and a minus 3 out here. This is going to give us some sort of internal shift. So this is going to move the graph over 1 unit to the right, and this number right here will move the graph down 3 units. So it will be very similar to the 2 to the x graph with these extra changes. So we'll go ahead and plot that. So let's make a table of values to verify some of these transformations that I'm talking about, a subject you'll study more in the future. So this minus 1 is going to move, get a better marker here. This minus 1 in the exponent will move the graph right 1 unit, and this minus 3 will move down 3 units. Okay, so we can move our graphs around our parent exponential function by adding and subtracting numbers. So doing a table of values in this case, okay, I'm going to go ahead and make my table of values. And I'm going to try to adjust the numbers so that I get nice outputs. So in this case, if I pick 1 for x, 1's a nice number because 1 minus 1 makes a 0 in the exponent, and 2 to the 0 makes 1. So then I'll have 2 to the 0 power minus 3. So that would be 1 minus 3, so I get minus 2. And I get the order pair 1, negative 2. And then let me go ahead and try 2. A 2 for x will give me 2 to the power 2 minus 1. So that would give me 2 to the power 1, which is 2 minus 3. So that would give me a negative 1. And then let me go ahead and try 3. If I put a 3 in the exponent for x, I get 2 to the 3 minus 1, which is 2 squared, which is 4 minus 3, so I get 1. And if I go ahead and try 4, 4 will give me 2 to the 3rd power, which is 8 minus 3. That gives me the order pair. That gives me a 5, so I get the order pair 4, 5. Okay, and then I'm going to try a 0, and 2 to the 0 power is 2 to the 0 minus 1 power is 2 to the negative 1, which is half, and then I get 1/2 minus 3, so I get minus 2 1/2. This is where it gets a little messy. Okay, so I'm going to go back and plot these all together on the same graph, and I can compare the differences. So 2 to the x minus 1 minus 3, I predict will be this graph, and it's going to move it over to the right one. So every point moves to the right one and down 1, 2, 3 units. So let's see if that correlates with the values I have. I get 1, negative 2. So 1, negative 2 is right here. So that's this point moved over 1 and down 3 units. That works. And then I have 2, negative 1. That's this point shifted. And then I have 3, 1. And then I have 4, 5. And then I have 0 and negative 2 1/2. So I'm going to get my general graph to be something like this. Okay. So what I have so far is I have a 2 to the x graph here, and this one is my 2 to the x minus 1 minus 3 graph. Okay, so that's another variation of the 2 to the x graph. Some other variations you might get involve putting negatives in front of the variable in the exponent, And what that does is give you the opposite x value. So it flips the graph over across the y-axis. And we'll take a look at how that works. And then if I have a negative in front of the 2 to the x, it'll flip the whole graph over the x-axis. So just labeling my axis here. Let's try this third graph right here. Let's go ahead and try f of x equals 2 to the negative x. Okay, one thing to note, this is also the same as, if you think about it, 2 to the negative 1 times x. So this is the same thing as 1/2 to the positive x power. Okay? So a lot of times you'll be given exponential functions in their fractional form, and you could always write their fractional form as a negative exponent. So this is 2 to the negative 1 power to the x power, which is equivalent to 2 to the negative x. These are exactly the same. So if we go ahead and do a table of values, we'll see that every x becomes its opposite. So I'm going to choose some x values that are already negative because the negative in the exponent will negate it. So if I choose negative 2, I get 2 to the negative of negative 2, which is 2 squared and gives me an output of 4. If I choose negative 1, I get 2 to the negative of negative 1. That becomes 2 to the first, which is 2. And then if I pick 0, I get 2 to the 0. So that is just 1. If I pick 1, I get 2 to the negative 1. And that becomes 1/2. And I could choose a lot more points to get a better sense of the graph. However, I already know sort of what's going to happen. I know it's going to flip every x to the opposite value. So this is my original 2 to the x graph, and it should just reflect across the y-axis. So looking at my points here, I have negative 2, 4, right around here. I'm going to move my 4. Negative 2, 4. I have negative 1, 2. I have 0, 1. Same point here. And then I have 1, 1/2. And you can see that it just goes this way. So this graph here is to the negative x. And just one more variation here. Let's go ahead and take a look at f of x equals negative 2 to the x. So if we do an xy chart, okay, if I pick 1, or I'll start with 0, 0 for x, I have negative 2 to the 0 power. That becomes negative 1. If I choose 1, I get the opposite of 2 to the first power, which is 2. If I put a 2 in there, which is a negative 2, excuse me. If I put a 2 for x, I get the opposite of 2 squared, which is -4. If I put a 3 in here, I get -2 to the third, -8. If I put a negative 1, I get opposite of 2 to the negative 1, which is negative 1/2. Okay. What happens is this will tell me that all my output values will be the opposite y value. So I'm going to have everything from my original 2 to the x graph moved into the negative y section. Or basically it will be reflected along the line, along the x-axis, the line y equals 0. So this reflects, we say it reflects across the x-axis y equals 0. And this, as I mentioned, I'll write it down, reflects across the y-axis. Okay, so what happens here is we end up with 0, negative 1, 1, negative 2, 2, negative 4, negative 1, negative 1 half, and that's a general trend. I could go further. But this is my graph, negative to the x. Now, an important property of exponential functions is something we're seeing in all these graphs, something called an asymptote. And it's when the graph gets closer and closer to a value, but never reaches that value, never crosses. If you notice the to the x graph, it gets closer to the x-axis, but never crosses. So what we have here is we have an asymptote. And this asymptote is the x-axis or at y equals 0. Okay? Now the same thing happens here on the other side. This is also an asymptote. And also over here we have an asymptote, even with it flipped. So when you see this behavior of an exponential graph where it gets closer and closer to a value but never crosses, that's called asymptotic behavior. So we have those for exponential functions and some other functions. Now the one that's a little different is this graph. Since you moved everything down 3 units, your asymptote is right here. So here you have an asymptote that is y equals negative 3. There's this invisible line that appears to be at y equals negative 3 that the graph seems to follow. So those are some standard examples of some exponential functions and how you graph them. So a good table of values, but also getting a sense for how the graph is looking like paying attention to the signs and the numbers and adding all the numbers and subtracted to your exponential function. So one last note on exponential functions is the properties. I'll leave off with a mention of those and something that you want to pay attention to when you're graphing. Okay, so the main properties of exponential functions. As with any function, we always want to identify what our domains are. So if you think about a typical exponential function, like f of x equals 2 the x, you could put any valid input for x and always get a valid output. So here you could put any real number, that's our symbol for real numbers, into x and always get a valid output. So the domain, I'll just say domain, is always all real numbers, or I'll just use our symbol. Okay, so we could put any real number value into our x inputs, as an independent variable. Okay, so we'll always get a valid output. And if you look at the graph, you'll see that your graph covers all the x values from left to right. Now the range, on the other hand, is a trickier subject. The range is going to depend on the function and vertical shifts. So for example, if I looked at the function to the x, And I just will redraw this sketch. I don't need to go into extreme detail, but just remembering some of the main points. 1, 2, 0, 1. So this was my to the x graph. There's y and here's x. And again, this is the asymptotic behavior. As it reaches the x-axis, it get closer and closer to a y value of 0, but will never reach it. So the range here would be from 0, not including 0 because it doesn't touch the value of 0, 0 to infinity. Okay, so here I'll have, this will include all my y values from 0 to infinity. Now the domain, as you can see, I'm just going to verify what I've put up here. The domain we could see is all real numbers, that the graph spans from left to right and will eventually cover every single x value. Okay, so it's really, your range is really dependent upon whether you're moving your graph up or down, because if I move it down 3 units, then my range will start from -3 to infinity. If I move it up a certain amount of units, it will depend on that value, and my range will span all the way up to infinity there. And also how you reflect them. Now the other properties that you'll be identifying are asymptotes. Okay. These are vertical lines or horizontal lines. The graph seems to follow. So it's going to depends on the function. So for example, i.e., we had f of x equals 2 to the x power again. The asymptote is y equals 0. Okay, very important. We saw that when we actually looked at the graph, and that's a good way to identify them if you're ever unsure. Look at your graph. Now the other properties are your x-intercept. You don't always have, but x-intercept is you find x when you set y equals 0. And for exponential functions, you may or may not have okay, these are crossings on the x-axis. So if we had our to the x function right here, you notice that there's no x-intercepts in this one. There's no x-intercepts. However, if I moved it down, I would get some x-intercepts, and I could find them by setting my y in my equation equal to 0. The same technique as we've done before. And lastly, our y-intercept. Again, it's going to depend on your function, but you find y when x is equal to 0, and you have at least 1. You have 1, I should say. So these are the crossings on the y-axis. So here we have our y-intercept. So we have a y-intercept, we have no x-intercept, and here we have an asymptote that is going to be y equal to 0. Those are some of our main properties for exponentials. So here is a graph of to the x again, a real quick little sketch. We did a more thorough example previously, but you could go through a very good example and then identify where your intercepts are, your asymptote, and state what your domain and range is. So you should be able to do that for any exponential function. especially when you're graphing. That really helps to understand its properties. All right, that's it for this lesson, and we'll move on in the next lessons to doing more properties. We'll look at applying more of these properties to exponential functions and look at solving exponential equations and introduce logs as well. All right, thank you.